Now we officially begin our limit process. So we're going to first start just graphically, numerically, working with functions we can graph or figure out how to graph based on all the ones you're used to, parabolas, rational functions, that kind of stuff. So we're going to start though first talking about what a limit is by investigating the behavior of one particular parabola nearby 2. So this is a nice parabola. You could find the vertex. You could do all that fun jazz. If you plug in 0, that would give you 0 squared minus 0 plus 2. So you go through positive 2. If you plugged in 2 itself, that would be 2 squared minus 2 plus 2. So your output would be 4, giving you this parabola. So what I want to do is I want to investigate the behavior around 2. What happens at 2 itself, I don't care. I want to know nearby 2. There we go. So we're going to use a calculator and we're going to plug in these particular values into this function here. So I'm going to go ahead and start by just typing it. I want to plug in 1.9. So that would give us 1.9 squared minus 1.9 plus 2. And so I get 3.71. So my output is 3.71. If I bump this up and I add an extra 9, my output is around 3.97. If I plug in a number even closer to 2, it's 3.997. Now, if I change this and go on the other side of 2, that would be 2.001 squared minus 2.001. And we get on this side about 4.003. I move a little further away and I take away one of these zeros and I plug in 2.01. My output is about 4.03. Move even further, my output is 4.31. Okay. So you can see as I'm getting closer and closer to 2 on either side of 2, my y values look like they're getting closer and closer to 4, okay? So what we can say is we can make f of x as close to 4 as we want by picking x sufficiently close to 2. So you see I can get super, super close to 4 when x is within a certain distance of 2, right? So what this means is we can say the limit of our function as x approaches 2 is equal to 4. So x is getting closer and closer to 2, your y is getting closer and closer to 4. Notationally, this is saying the limit as x approaches 2 of this particular parabola is equal to 4. So this is what we want to explore. As x gets close to some number, what is happening for the output of your function? Okay? So this leads to our definition of a limit. Suppose f of x is defined when x is near the number c, but not necessarily defined at x equals c. Then we write the limit of this function as x approaches c is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to c on either side, but not equal to c, okay? So this is the idea. I look at what happens around 2. For x around 2, what is your y approaching? So around 2, our y is approaching 4. What happens at 2, I do not care about. I only care what happens around it. So another notation you're going to see possibly is this arrow. This arrow also indicates approaching. okay? So the things to keep in mind when we're talking about limits is first, we never care what happens at the particular value. So as x is approaching c, I don't care what happens at c when I'm evaluating a limit. We're only concerned nearby. Second thing, the function may actually be undefined, and that's okay. The limit can still exist even if the function does not exist at c. And the last thing is the function needs to be going to a single finite value for the limit to exist. So kind of to give you an example, we're going to look at three functions. First one, if I approach 1 on either side, my y values look like they're getting closer and closer to 2. So I could say my limit as x approaches 1 is 2. If I change this figure slightly, and instead of having a closed-in circle here, I make it an open circle. Does not change a single thing, because when I get close and close to 1, as I trace this graph, my y values are still getting closer and closer to 2. If I make it so that f of 1 is 1 instead, still changes nothing, because when I'm approaching 1 on either side and I'm tracing what's happening on my graph, my y values are getting closer and closer to 2. So in each figure, as x approaches 1, my y is approaching 2. So we could say the limit as x approaches 1 for this function is equal to 2. Even though f of 1 is completely undefined in the second picture, and in the third picture, my function value is completely different than my limit. Perfectly okay, right? So one thing that students also tend to fall into a trap of is in that first problem, I was able to just plug in numbers and kind of get an idea. So we think those numerical charts are always going to work, but they can be deceiving. They're really great for us to start out with because that's something I can handle before I come up with all of these different laws I need to. But they can also hinder you in the harder problems. So let's look at an example. Let's try to evaluate this particular limit. We're going to see what's happening for this function as x gets closer and closer to 0. So 1, kind of close to 0, not really. We'll do a third, a fifth, a tenth, and 1/100th, so 0.01. We're going to get closer and closer to 0. And so these are numbers I can actually evaluate without using a calculator. I can do it in my hand. So I'm going to plug in these values. This would be pi divided by 1, so sine of pi, which is 0. If I divide by a fraction, remember it's multiplying by the reciprocal. So this would become sine of 3 pi, also 0. This would be sine of 5 pi, which 0. Sine of 10 pi, also 0. Sine of 100 pi, also 0. So it really seems like my limit is going to be 0, but that's not actually the case in here. So let's see. So let's take a look. If I go ahead, let's look at sine of, we want to do pi divided by, let's pick a number that I can't plug in as nicely. Say like 0.27. That doesn't give me 0. It's just, I can't do this in my head, but 0.27 is close to 0. So this is a problem that's going to happen somewhat frequently. It seems like sine of pi over x is equal to 0 as x approaches 0. But really, I can pick a ton of values in between that make sine of pi over x equal something else. 1. In this case, I got 0.2 as an output, not 0. Because if you actually look at the graph of this function, it's going to oscillate back and forth. If you plug it into a calculator, this is just going to be completely covered in because this graph is just jumping over and over and over again. And that's not so good. So pretty much to start, these charts are going to be helpful. But moving forward, we want to figure out more precise ways to calculate limits, okay? But right now, we're going to work with graphs. We're going to work with this process. But then we'll learn some limit laws and how to evaluate analytically. So in these next 3 examples, we're going to use the graph to evaluate the limits. So we have a nice piecewise function, and we want to see what happens as x approaches 2. So for every other number, I'm going to graph this line, but at 2 itself, my output is going to be 0. So that is just a nice line. You know, graphing is always not super fun either. If I plug in x equals 0, your y is 4. X equals 4, your y is 0. If you try to plug in 2, you'll get an output of 2, but it has a hole at that particular point. Okay. So right here, we have a hole at 2, 2. And then if I plug in x equals 2, your output is going to be 0 based on this second piece. So when I'm approaching 2 and evaluating this limit, on the left-hand side, if I trace the curve, it looks like my y is still going to 2. On the right-hand side, I'm tracing my curve. I'm still getting 2. So ultimately, this limit does equal 2, even though I've got a different output at 2 itself. That's okay, because it looks like my graph is going to 2. Okay. For these next 2 functions, we're going to work with our rational functions a bit. So for both of these, those have a vertical asymptote at 5. And if you remember what the graph of this looks like, it's that reciprocal function. So it has this kind of shape. Okay. So if I approach 5 from this side, my y values are growing more negative. If I approach 5 from this side, my x values are growing positive and positive and positive. So ultimately, I don't approach a single finite value. It's doing 2 different things, and it's blowing up on both sides. So what we would say is that this limit does not exist, and you can use DNE to represent that, because we do not approach a single finite value. Okay. For this next problem, it's similar in shape, but because it's got that square in the bottom, here's 5 itself, the bottom is always going to be positive. So really your graph goes up forever on both sides. So if I approach 5 from this side, my y value is blowing up. As I approach 5 from this side, my y value is also blowing up. So technically you could say does not exist because it's finite, not a finite value. But what we would rather say is this limit is equal to positive infinity, because on both sides, I'm blowing up and I'm growing larger and larger and larger. So when you can put in infinity, you want to make that distinction. Okay? Where here, it's doing 2 different things on either side. So definitely this does not exist. Right? Okay, let's try a piecewise function. We are going to use this absolute value function a ton, so you definitely want to make sure you know its formal definition. We're going to try to graph this, and we want to recall this absolute value as piecewise. So the absolute value of x is going to be exactly x if x is greater than or equal to 0. So if I take the absolute value of 2, it's still just 2. So you get the same thing back. But you have to change the sign if you input a negative number. So like -2 gives you an output of +2. So I have to negate what I put in. Okay. So if I'm dealing with the absolute value of x over x, I no longer am going to have the 0. That's okay, because that causes me to divide by 0. But pretty much in all of these, I'm going to just divide everything by x and get rid of that equality part. So this is also a piecewise function where I take both and divide by x, now exclude 0. So this gives me 1 or -1, depending on whether we're positive or negative. So the graph of my function will look like this. It's a nice piecewise. Make this a straight line. Okay, so 1, 1, 1, 1. And my graph will give us +1 for positive numbers, -1 for negative numbers. So as we approach 0, because that's what we're trying to take the limit as x approaches, on this side, it's going to -1. On this side, it's going to +1. Let me use a different color so you can see that. On this side, going to +1. So as x is approaching 0, this graph does not approach a single finite value. So we would say this limit does not exist. Okay? So the last thing we're going to do is now a more formal definition, because our first one is a little wishy-washy. And I won't lie, this process is going to be hard. It's probably going to look really confusing, but you want to keep that idea intact. Your y values get really close to the limiting value when x is nearby the number you're taking a limit of. So go back up here. When we're near 2, the y is near 2. Okay? So let's try to break down this formal definition of limit. We use that phrase, f of x becomes arbitrarily close to L in our definition. So basically, I can make my y values as close to the limiting value as I want. So we want to come up with a more precise way to talk about this. So we're going to let this kind of look in E. It's a Greek letter epsilon. This is going to represent a small positive number. This phrase, f of x becomes arbitrarily close to L, means our function value lies within this particular interval. That interval is a little messy looking, so instead we're going to look at it using absolute values. If I look at the difference between my function values and the limiting values, it is super tiny. So that is all this absolute value is telling us. The difference between f of x and the limit L is very small. Okay? Now this has to happen when x is close to c. So I need to come up with another inequality that really talks about that in the same manner. So the phrase x sufficiently close to c means there's a positive number, which we're going to call delta, which kind of looks like an S, such that x lies within this particular interval. Really, all that's saying is, again, using absolute values, if you look at the distance between x and the number we're approaching c, that distance is delta away. So pretty much x is within delta distance of c, but also has to be positive so it can't equal c, which is what we want in the limit. I don't care what happens at that specific number, just nearby. Okay? So this is our formal, precise definition for a limit. We're going to let f be a function defined on an open interval containing c. Don't care what happens at c. And L is going to be a real number. If no matter how small I make an epsilon, there exists a delta so that if my x is delta distance from C, my y is epsilon distance from L. If no matter what that distance I give you, you can find x's nearby, then I can say the limit as x approaches C for my function is equal to L. Okay? So I'm going to go back up to this first example because it'll be a little bit easier to talk with numbers. I know it can be hard to dissect everything when you're just given a bunch of letters. Throw in those Greek letters too. But pretty much if you look at the difference in the y values between my limiting value, I know as x approaches 2, my y is approaching 4. The difference between these two is 0.003. So that would be my epsilon. If I want the difference between my y and my limiting value to be 0.03, the difference in my x's has to be 0.001. So this would tell me if my epsilon is 0.003, my delta needs to equal 0.001 to guarantee I'm within that distance. And same thing if I go on the other side. This distance is 0.003 in the y values, and that delta distance is 0.001. So if I give you epsilon as 0.003, your delta has to be 0.001. So that 2 minus whatever that x value is will be close enough to 2. Okay? So this is our idea and this formal definition, and we're going to try an example. Okay, so you don't have many of these on your homework, I promise. Do your best with them. It is a very difficult concept, so don't worry if you are struggling. We are told the limit as x approaches 1 of this function is equal to 4. We want to find a delta so that if I look at the difference in my function and my limiting value, that is guaranteed to be less than 0.1 whenever my x is delta distance away from 1. Okay, so pretty much I kind of need to just figure out what delta I have to plug in here given this epsilon. So I'm going to match everything up to this limit. So here, the C that x is approaching is 1. The function we're dealing with is 2x plus 2. My limiting value is 4. And this epsilon is 0.1 because that's the difference between my function and my limiting value. Okay. I need to establish an inequality like this, but I'm already given an inequality. So I want to find a connection between these two. That's going to be our goal. So to find delta, try to establish a connection between the absolute values or between the given absolute values. So we are told the absolute value of 2x plus 2 minus 4 is less than 0.1. And we need to really manipulate it to be something like this. Okay? So hopefully this x minus 1 in absolute value will pop up somewhere from here. So I'm going to work with the one that's given to us. So notice, if I take the absolute value of 2x plus 2 minus 4 is less than 0.1, and I manipulate this, those parentheses do absolutely nothing. So really this is 2x minus 2 inside this absolute value. And then they both have 2 in common. We can pop that out to give us 2 times x minus 1. And then one nice thing about absolute values is you can take the absolute value of each individually. And notice what we get, the absolute value of x minus 1. So if I divide this side by 2, I got to do the same thing over here. This tells me the absolute value of x minus 1 needs to be less than 0.5. Okay. And so the delta I need is 0.5. Okay. So if delta is equal to 0.05, we can guarantee the absolute value of 2x plus 2 minus 4 is less than 0.1 when x minus 1 is less than 0.05 and also greater than 0 because we don't want x and 1 to be equal for the limit. Okay? So that's going to be your goal. You're going to start with one of the inequalities that's given to you and try to manipulate to get the other one. Okay, so try your best with it. If you have questions, let me know.